Quasi-hereditary algebras, lecture 19, graded generalizations. Let us talk about the general setup of graded algebras. Let K be a field, and let A be an associative and unital K algebra. Let G be an additively written abelian group whose unit element is 0. Definition: a G gradient on A is given by a decomposition of A as a direct sum of subspaces A sub G, which are indexed by elements little g in our group capital G. So here each AG is a subspace of A, and the following condition is satisfied. If we take an elements from A sub G and multiply them with an elements in A sub H, we will end up in A sub G plus H for all G and H in our group G. For example, any algebra A can be trivially graded by declaring A0 to be A and A sub G to be 0 for all non-zero elements G in our abelian group. We will mostly consider the case where our abelian group is the group of integers, but some things we will say also in the general setup. Here are some further examples. Example 1. Consider the polynomial algebra A over K in the variable x. For a non-negative I, define A sub I as a linear span of the ith power of x. And for a negative I, define A sub I as 0. Then, this defines on the polynomial algebra the structure of a z-graded algebra, since x to the power I times x to the power j is equal to the x to the power I plus j. So this is the natural grading on the polynomial algebra. Example 2. Consider the group algebra A of our abelian group G over K. For an element little g in our group G, define A sub G as a linear span of this element G inside our group algebra. And this also then trivially defines on the group algebra the structure of a G-graded algebra. Next, let us consider the case of quiver algebras. Let Q be a quiver, and K of Q be the path algebra of Q. Then this path algebra is naturally graded by the lengths of the path. This means that the subspace KQ sub I is the linear span of all passes of lengths I, if I is a non-negative integer, and if I is a negative integer, then this is defined to be 0. So for example, if we take the quiver Q to be just one vertex and one loop in this vertex, then the corresponding path algebra K of Q is isomorphic to the polynomial algebra over K in the variable alpha. So here alpha is our loop. And the gradient on K of Q by path lengths then coincides with the gradient on the polynomial algebra by the degree of alpha, as considered on the previous slide. Here is yet another example. If our quiver Q consists of two vertices 1 and 2, and one arrow beta from 1 to 2, then for the corresponding path algebra K of Q, the zero space KQ sub 0 is a span of the trivial passes epsilon 1 and epsilon 2, so these are the trivial passes at the vertices, and the subspace KQ sub 1 is the span of beta. Beta is an arrow, it has degree 1. There are no other passes in Q, so KQ sub I is 0 if I is different from 0 and 1 in this example. Now let us talk about homogeneous ideals. Let A be a G-graded algebra. Definition: an ideal I of A is called homogeneous, provided that I is a direct sum of its homogeneous components I sub j, where j is an element in our index in abelian group, and I sub j is defined as I intersected with A sub j. Given a homogeneous and ideal I of a G-graded algebra A, the quotient of A modulo this homogeneous ideal naturally inherits a G gradient from the algebra A. For example, let us consider the quiver Q, which has two vertices 1 and 2, an arrow alpha from 1 to 2, and an arrow beta from 2 to 1. Then we have its quiver algebra, which is naturally graded by the lengths of a path. So here we can consider the ideal in this quiver algebra, which is generated by the path alpha beta. So that's a path of length 2, so it belongs to the second degree homogeneous component. An ideal generated by a homogeneous element is a homogeneous ideal, and then the quotient of the path algebra by this ideal will then be a graded algebra, which will now be finite dimensional. Its zeroth homogeneous component consists of linear combinations of the trivial passes at the vertices. Its first homogeneous component consists of the linear combinations of alpha and beta. Its second homogeneous component consists of the linear span of beta alpha, and the rest homogeneous components are 0. Now let us talk about the orbit categories. Let C be a k-linear category. Recall that this means that each Hom space Cij is a vector space over K, and that all compositions are K bilinear. Assume that our group G acts on C by automorphisms, and also assume that this action is free, in the sense that the stabilizer of each object is trivial. Then we can define the corresponding orbit category C modulo G as follows. The objects of this category are the G orbits of objects of C. Now, in the category C modulo G, a morphism from the orbit of I to the orbit of J is a quotient of the direct sum of all Hom spaces CST, where C belongs to the orbit of I and T belongs to the orbit of J, modulo the subspace generated by all morphisms of the form phi minus G of phi. So phi is a morphism in some CST, and we take phi and subtract G of phi in this big direct sum. And the rest of the structure is inherited from the structure on C. Our main observation is that orbit categories are naturally graded. So let C and G be as above. From the definition of the Hom space in the orbit category, we see that in our orbit category, the Hom space from the orbit of I to the orbit of J is isomorphic to the direct sum over all elements G in G of the Hom sets in C from I to G of J. Let us fix one representative I in each orbit of G acting on objects of C. Then, for G in G, we define the elements in the set C of I to G of J to be of degree G. And this makes the orbit category into a graded category. So this means that in our orbit category, the Hom space from the orbit of I to the orbit of J is a direct sum of the homogeneous components. And that the multiplication in the orbit category acts additively on the indices of these homogeneous components, just like for the graded algebra. Here is an example. Consider the path category of the following quiver Q. So the vertices in this quiver are integers, and for each I we have one arrow from I to I plus 1. And that's it. The abelian group of all integer acts on this quiver by shifts. So we send the vertex I to the vertex I plus n. So n is an integer here. And of course this induces a free action of our group Z on our path category C. And the orbit category has one vertex, because there is only one orbit on vertices for this action. And then the morphism algebra of this vertex is exactly the polynomial algebra, if we take as the variable for this polynomial algebra the arrow alpha from 0 to 1. And of course, by definition, the degree of this alpha is 1. So as the orbit category, we get exactly the category with one object, whose endomorphism algebra is the polynomial algebra, with the natural gradient. Now let's see how we can go back from the orbit category back to C. So let C be a G-graded K-linear category. Then we define a new category C tilde in the following way. Objects of C tilde are pairs I, G, where I is an object of C and G is an element in our group G. And the Hom set in C tilde from I, G to J, H is by definition equal to the homogeneous part in the category C for Homs from I to J, and we take the homogeneous part of degree H minus G. And the rest of the structure is simply inherited from the corresponding structure on C. Then the group G acts on our C tilde by sending the object I, G to the object I, G plus H. So here H is an element in G which acts on our object. And the action on morphisms is the obvious one, it's given by the identity maps. If we shift the second index by the same H, it will cancel out here in the definition. And then it's very easy to see that this action is free on objects, and that the corresponding orbit category C tilde modulo G is isomorphic to our original category C as a G-graded category. Now we have described how to go from categories with a free G action to G-graded categories and how to come back. Here is an example. Consider the polynomial algebra as an algebra that is Z-graded in the obvious way, by the degree of x. Then we can view this algebra as the endomorphism algebra of an object in a K-linear category C with one object. So let that object be I. Let us now construct C tilde. So the objects in C tilde are pairs I, K, where K is an integer. So since I is unique, we just forget it and we identify such object with K. If K is greater than or equal to M, then the Hom set in C tilde from M to K is the span of x to the power K minus M, right? And this implies that C tilde is isomorphic to the path category of the quiver, which we already saw before. So the vertices are the integers, and from each I we have an arrow to I plus 1. So this is how we come back from a graded category to a category with a free action of G. Some comments and remarks. Let A be a finite-dimensional G-graded K algebra. So we can view A as the endomorphism algebra of an object in a K-linear category with one object. Then we have the corresponding category C tilde, which we constructed above. And if the group G is infinite, then the path algebra of this C tilde will be infinite dimensional. It's no longer finite dimensional. If we assume that our original category A was quasi-hereditary or stratified, then we can look at this structure and compare this structure with the analogous structure for the category C tilde. And that's what we will explore on some examples later on in today's lecture. So now let us talk about graded modules. Let A be a finite-dimensional G-graded K algebra. And A module M is G-graded, provided that we can write M as a direct sum of the subspaces M sub G, where G is an element in our indexing group capital G. So M sub G is a subspace of M, and the following condition is satisfied if we take A sub G and we apply it to M sub H, we will end up in M sub G plus H for all G and H in the capital G. So we have the category AG capital mod consisting of all graded A modules, and where the morphisms are homogeneous homomorphisms of A modules that have degree 0. So that's important to have here homogeneous maps of degree 0, for otherwise it's very difficult to get an abelian category. And such morphisms are usually denoted as Hom sub A with a little h and not a capital H in front. And we also have the natural forgetful functor from graded modules to usual modules that simply forgets, ignores the grading. And we have the following subcategories of the category of graded modules. We have A, G, little mod, consisting of all finitely generated modules. A, LFG mod, consisting of all modules. LF means locally finite dimensional, so it consists of all graded modules M, such that the dimension of each homogeneous component is finite. And then we have the category AFG mod, consisting of all finite dimensional modules M. Now let us talk about gradable modules. A warning: the forgetful functor from graded modules to all modules is usually not dense. And an A module is called gradable provided that it is in the image of this forgetful functor up to isomorphism. The group G acts on the category of all graded modules by isomorphisms, which are usually denoted that H acts by H in these triangle brackets, and this simply shifts the gradient of the module. If we have a graded module M and H in G, then M of H in triangle brackets and then the homogeneous component little g of that module is by definition equal to the homogeneous component g plus h of the original module M. And the action on morphisms is the trivial one, it's just given by the identities, which we also shift according to the shift of the gradient. If a module M is gradable, then any M tilde, any graded module M tilde, which becomes isomorphic to M after forgetting the grading, is called the graded lift of M. It is very easy to prove that graded lifts of indecomposable, gradable finite dimensional modules are unique up to isomorphism and shift of grading. So even uniqueness is only up to isomorphism and shift of grading. Now let us talk about positively graded algebra. Let A be a finite dimensional Z-graded K algebra. Definition: we will say that A is positively graded provided that all homogeneous components of negative degree are 0 and the radical of A equals the direct sum of all positive homogeneous components. For example, the natural gradient on the truncated polynomial algebra kx modulo x to the power k is positive. So the natural gradient means that we put the field k in degree 0 and the variable x in degree 1. Example 2. Any finite dimensional quotient of a path algebra of a quiver by a homogeneous ideal is positively graded if we put all trivial passes in degree 0 and all arrows in degree 1. And example 3, any finite dimensional semi-simple algebra is positively graded if we put all of this algebra in degree 0. Now let us discuss grading on structural modules. Let A be a finite dimensional positively graded K algebra. Then A0, which is isomorphic by the definition of a positively graded algebra to A modulo radical A as a module, is a graded semi-simple module which contains all simple modules as direct summands. So this means that all simple A modules are gradable. Next, it is very easy to see that for positively graded algebras there is a decomposition of the identity into a sum of mutually orthogonal primitive idempotents, all homogeneous of degree 0. This means that all indecomposable projective modules Pi, which have the form A times epsilon I, so the point is that epsilon I is now a homogeneous element, so these modules inherit a G gradient from the gradient on the algebra A and hence are also gradable. So simples are gradable and indecomposable projectives are gradable. Next, let us note that if we have two gradable A modules M and M tilde and N tilde are some graded lifts of M and N, then the space of all ungraded homomorphisms from M to N as A modules can be written as a direct sum of the spaces of all graded homomorphisms from M tilde to all possible graded shifts of N. So using this, it follows that the traces of gradable modules in gradable modules are gradable submodules, and hence all costandard and standard A modules are gradable because they can be defined using such traces, or kernels of maps to such traces. Now we can come to the situation of graded quasi-hereditary algebras. So let A be a finite-dimensional, positively graded K-algebra, which is additionally quasi-hereditary. On the previous slide, we saw that in this situation, simple, projective, and standard modules are gradable, and similarly, injective and costandard modules are also gradable. One additional class of structural modules which each quasi-hereditary algebra has is the class of tilting modules. And in order to discuss gradability of tilting modules, let us note the following. If M and N are gradable A modules, with some graded lifts M tilde and N tilde, then the space of all first extensions from M to N is a direct sum of the space of all first extensions from M tilde to all possible shifts of N tilde. And let us recall that in decomposable tilting A modules are constructed starting from standard modules and then doing recursively the universal extension procedure. So we take the universal ext1, take the corresponding extension, and proceed in this way. And because of the previous sentence, it follows that all indecomposable tilting A modules are gradable. A direct consequence is that the Ringel dual of A, which is the endomorphism algebra of gradable modules, inherits a natural Z grading. One small warning, this new Z grading on the Ringel dual does not have to be positive in general. And also there is some freedom in fixing the graded shifts of the graded lifts of the indecomposable tilting modules. So indecomposable modules can be lifted to graded modules up to gradient shift. And then, since we are free to fix it in some way, it can affect the grading on the Ringel dual. So let us now discuss the standard graded lifts for structural modules over quasi-hereditary algebras. So let A be a finite-dimensional, positively graded K-algebra, which is quasi-hereditary. Then, as we have already seen, all structural A modules are gradable. So the following graded lifts of structural A modules are called standard. So we can take the graded lifts of simple modules and concentrate them in degree 0. So that's the standard thing. Next, we take the graded lifts of indecomposable projective modules such that their tops are concentrated in degree 0. So this means that the home from the indecomposable projective module to its simple top is a morphism in the category of graded modules. Next, the graded lifts of standard modules are such that their tops are concentrated in degree 0. Again, the home from the indecomposable projective to the corresponding standard module in the graded version is the home in the category of graded modules. Graded lifts of indecomposable injectives are such that their sockles are concentrated in degree 0, and similarly graded lifts of costandard modules are such that their sockles are concentrated in degree 0. And finally, the graded lifts of indecomposable tilting module is such that the natural inclusion of the corresponding standard module into this tilting module in the homogeneous map of degree 0 is a home in our category of graded modules. Let us do one example. Consider the algebra A given by the quiver with two vertices 1 and 2, one arrow alpha from 1 to 2, and one arrow beta from 2 to 1, and the relation that alpha after beta is 0. So here are the pictures which show the standard graded lifts of all structural modules. So the simple module L1 is just 1 concentrated in degree 0. The simple module L2 is 2 concentrated in degree 0. The indecomposable projective module P1 has simple top 1 in degree 0, and then it has 2 in degree 1 and 1 in degree 2. The indecomposable projective module P2 has simple top 2 in degree 0 and then 1 in degree 1. That's Sokol. Delta 1 is simple, so it lives in degree 0. Delta 2 has top 2 in degree 0 and then the Sokol 1 in degree 1. Delta 2 is the same as P2. Next, the indecomposable injective module I1 has Sokol 1 in degree 0 and then 2 in degree -1 on top of it, and then the top 1 in degree -2. The indecomposable injective module I2 has Sokol 2 in degree 0 and 1 in degree -1 on top of it. Nabla 1 is simple, so it's 1 in degree 0. Nabla 2 is I2, so it has Sokol 2 in degree 0 and 1 on top of it in degree -1. T1 is simple, so it's 1 in degree 0. And T2 has delta 2 as a graded submodule, so it has 2 in degree 0 and then 1 in the Sokol in degree 1 and 1 in the top in degree -1. It is interesting to point out that in this picture the same module appears 3 times, and that's P1, which is isomorphic to I1 and which is isomorphic to T2 as ungraded modules, but their graded lifts as projective, injective, and tilting are different. So for projective module we put top in degree 0, for injective Sokol in degree 0, and for the tilting we put the middle in degree 0. Let us now look at the previous example from the perspective of the covering of the corresponding quiver. Consider the K-linear category C, which is given by the following quiver. So we have vertices 1 sub 0, 2 sub 0, 1 sub 1, 2 sub 1, and so on. We have 1 sub I and 2 sub I, where I is an integer. Then we have the arrow beta I from 2 sub I minus 1 to 1 sub I, and we have the arrow alpha I from 1 sub I to 2 sub I plus 1. So this quiver is not connected, so it's a disjoint union of 2 connected components. And also let's take the relation that alpha I after beta I is equal to 0 for all I. Then the group Z acts on this K-linear category C by isomorphisms, and this action is induced from the following action on the quiver. So the element n, an integer n, sends a vertex 1 sub I to the vertex 1 sub I plus n, the vertex 2 sub I to the vertex 2 sub I plus n, the arrow alpha I to the arrow alpha I plus n, and the arrow beta I to the arrow beta I plus n. So an integer n just shifts the indices of all our objects in our quiver. And of course, directly from the definitions, we see that this action is free. Now, if we compute the orbit category for this category C and this action of the group Z, we will get exactly the quiver which defined the algebra A from the previous example. Indeed, so we have the orbit 1 sub I, so this is the orbit of 1s, then we have the orbit of 2s, then we have the orbit of alphas and the orbit of betas, and both alpha and beta have degree 1, because alpha goes from 1 sub I to 2 sub I plus 1, so it has degree 1, and beta also goes to 2 sub I minus 1 to 1 sub I, it has degree 1. So this is the universal covering of the previous example. Let's make some remarks by comparing the original quiver and then its universal covering. We know that the new category C is directed, really. If we look at this quiver, we see that all arrows go in one direction. So this quiver is directed, but of course its algebra is infinite dimensional because we have infinitely many vertices. So that's a general feature for positively graded algebras. So we have the category which is directed when we take the universal covering of a positively graded algebra, but the corresponding path algebra will be infinite dimensional. We also can see that the quasi-hereditary structure on the original category A does not come from the quasi-hereditary structure on the universal covering C, and this is because C being directed has a trivial quasi-hereditary structure where standard modules are simple. And in category A, standard modules are not necessarily simple. So here are some problems and questions at the end. Problem question 1. Check with all details that C tilde modulo G is isomorphic to C as a G-graded category. Problem question 2. Prove with all details that graded lifts of indecomposable gradable finite-dimensional A modules are unique up to isomorphism and shift of grading. Problem question 3. Prove with all details that, for a positively graded finite-dimensional algebra A, there is a decomposition of the identity into a sum of mutually orthogonal primitive idempotents, each idempotent being homogeneous of degree 0. Problem question 4. Prove with all details that if we have two gradable A modules M and N, and some graded lifts M tilde and N tilde of M and N respectively, then the space of all A homomorphisms from M to N is a direct sum of the spaces of all graded A homomorphisms from M tilde to all possible shifts of N tilde. And problem question 5. Prove with all details that all indecomposable tilting A modules for a finite-dimensional positively graded quasi-hereditary algebra A are gradable. Thank you very much and see you next time.